dignitaries, faculty members, researchers, our students, and other interested persons following the webinar. Myself, Shamuduti Haldar, Assistant Professor of the Department of Women's College. Our college is a glorious milestone in the history of education of women, not only in Hooghly district, but also in the state of West Bengal. It is the 6th academic institution in the district and is the first women's college of the district, and also is the largest women's college of Bardhan University. So we feel proud of our institution. In our department, 4 teachers, Dr. Gurudas Bishwas, Sumitra Ghosh, Rima Datta, and me, we really very glad to organize this national level webinar on mathematical modeling and its real world applications in this critical pandemic situation due to COVID-19 throughout the world. Today, we are very proud to have 3 nice speakers, Dr. Nandudulal Boiragi, Dr. Kunal Chakraborty, and Dr. Neelam. I express my heartfelt gratitude to all the honorable speakers for their assent to spare some time for us within their busy schedule. We really benefited a lot of our advisory members, Dr. Tapan Kumar Kaur, Head of the Department of Mathematics, IST Shibpur, Dr. Shati Mukhopadhyay, Professor of the Department of Mathematics, University of Bardwan, and Dr. Shamulina Goswami, IQAC Coordinator and the Head of the Department of Geography of our college. We are also very happy for the response of a huge number of participants. I also express my heartiest thanks to all of you for their interest, and please stay with us throughout the session. Now our Honorable Principal Madam, Dr. Shima Banerjee, will give the welcome speech. She took responsibilities of this college as a principal from the post of Associate Professor of the Department of Economics of this college in the year 2015. She is very enthusiastic. Without her inspiration, it could not be able to arrange such a program. I request her to say a few words. Principal Ma'am, please. Madam, please say something about our webinar.
Thank you, Shamuduti. Good morning, everybody assembled here today to participate in a one-day national level webinar organized by the Department of Mathematics, Hooghly Women's College, in association with the IQAC of the college. It is a glorious moment to extend my warm wishes on behalf of the Mathematics Department to all the participants and the invited speakers of today's webinar. The topic is mathematical modeling and its real-world applications. From last December 2019, the mankind is passing through an ever-seen crisis where social distancing, lockdown, new normal are the new concepts incorporated in our daily life all over the world. In spite of all the odd, we are assembled here in this webinar platform today to enrich ourselves. Especially, this is applicable for the students of mathematics. I extend my heartiest thanks to all the invited speakers who have agreed to share their knowledge in this webinar. The speakers, 3 speakers, already Shamuduti has mentioned. Nandudulal Boiragi, Senior Professor, Department of Mathematics, Jadavpur University, West Bengal. Dr. Kunal Chakraborty, Scientist E, INCOIS, Hyderabad, Ministry of Earth and Science, Government of India. And Dr. Neelam, Assistant Professor, Department of Applied Mathematics, Delhi Technological University. I also extend my heartfelt thanks to all the participants for registering themselves in this webinar to make it a great success. And last but not least, I must mention that in these trying times, our mathematics department has organized such a webinar related to a contemporary issue of mathematics. So I wish a grand success of this one-day national webinar. I want to over the microphone to Dr. Shamuduti Haldar. Shamuduti, please proceed. Shamuduti, please proceed.
Hello, thank you, madam. We are now eagerly waiting to hear the speech of our invited speakers. Our Honorable Speaker, Dr. Nandudulal Boiragi, Professor of the Department of Mathematics, Jadavpur University, is a renowned speaker. He completed MSc from Jadavpur University and got PhD from this university also. He is the coordinator of the Center for Mathematical Biology and Ecology, Department of Mathematics, Jadavpur University. He has published around 100 research papers in different reputed national and international journals in biomathematics. He has published some books also on biomathematics. He has guided a lot of PhD scholars and received many awards, projects of state and central government. So we are glad to have such a wonderful speaker. So we don't waste our time. I request Dr. Boiragi to deliver his lecture on dynamic perspective of COVID-19 pandemic. Sir, please.
Okay, thank you.
Sir,
Yeah.
I request you to deliver lecture. So I waiting for you.
Is it visible?
Yes, sir. It's visible.
I am audible also.
Also audible.
Good morning, everyone. I hope all of your family members are well and safe. First of all, I would like to thank the organizers for giving me this opportunity to speak in the national webinar on mathematical modeling and its real-world application. The world has been passing through an extraordinary crisis. Just now, the respected principal has also cited this word that the world is passing through an extraordinary crisis. During the last few months, due to an extraordinary disease called COVID-19. This disease is extraordinary because our immune system is unable to fight against this disease. And it has a stunning transmission capability from human to human. And the crisis is extraordinary because it has not only caused a global medical crisis, but also put the world into unprecedented economic and social crisis. The story began on the last day of 2019 when China informed the World Health Organization about a new disease that causes unusual pneumonia. The virus crossed the border of China and disseminated in at least 23 other countries, including USA, Italy, UK, and India, through international travelers in the first month of 2020. The outcome was so intense that WHO had no option but to declare COVID-19 a global pandemic on March 11. The first case of COVID-19 in India was detected on January 30. A student who returned to Kerala from Wuhan, the birthplace of COVID-19, was tested positive first. And look at this table. This table compares the worldwide epidemiological data of COVID-19 as of today with the data of 31st January 2020. On January 31st, the number of affected countries was 23 with 2011 infected cases and only 43 deaths. As of today, that is the 8th September 2020, 216 countries and territories are affected with this disease, with about 2.75 crore infected cases and around 8,96,000 deaths. And if you look at the data of our country, the number of confirmed case as of today, it is around 42,78,000, and the number of deaths is around 73,000. And the case fatality ratio of India is around 1.7. The case fatality ratio percentage means that around 1.7 people dies due to this infection out of 100 positive cases. However, this number is 3.2 in case of world. That means it is almost double. So India has case fatality ratio around 1.7%, while the world has 3.2%. This is a model picture of coronavirus. I have taken this picture from the internet, and we all know that the disease is called COVID-19, and its causative agent is SARS-CoV-2. This name was given by International Committee on Taxonomy of Viruses on 11th February 2020. You can see that there are many spikes, these red colors, on the cell surface of a coronavirus, which give a look of a crown. That is why the virus is called a coronavirus. The virus uses this spike, this is also the S protein, as a key to open the cellular door of its host cell and enters into the cell. The symptoms of this disease are similar to the symptoms of common flu. Infected individuals may have fever, dry cough, shortness of breath, and fatigue. Transmission of infection occurs through direct contact or inhaling the infected droplets. It may also pass through the objects in the immediate environment around the infected persons. And we all know that there is no specific drug or vaccine for 2019 COVID till today. The only way to reduce human-to-human transmission of these highly contagious diseases is non-pharmaceutical interventions, which include individual hygiene, cough etiquette, safe distancing, and of course the lockdown. One interesting question is why lungs are severely infected or affected by this disease. S2 is a protein found on the surface of many cell types, and the S protein of coronavirus has a strong affinity or binding affinity to this S2 protein. In the lungs, S2 is highly abundant, and therefore lungs are mostly affected by this disease. It is reported that individuals having hypertension, diabetes, and heart disease may have higher level of S2 protein, and therefore these people are more prone to SARS-CoV-2 infection. COVID-19 infection may be classified into mild, severe, and acute cases, depending on the severity of the infection. About 81% of the COVID-19 cases are mild or asymptomatic. They do not require ICU treatment. About 14% cases are severe and they need ICU treatment. Their breathing rate per minute is higher than 30, whereas the normal rate is 12 to 18. And their oxygen saturation level is less than 93%, whereas the normal range is 95 to 100%. 1% cases are acute and they show respiratory failure and multiple organ dysfunction. Out of this 1%, around 35 to 50% patient die due to this COVID infection, and we lost them forever. The recovery rate or recovery time in case of mildly infected COVID-19 patient is around 1 to 2 weeks. However, the recovery period for severely infected COVID-19 cases may vary from 2 to 4 weeks. Before going into the mathematical model, I would like to introduce some terminologies. The first one is latent period. It is defined as the time between the occurrence of infection and the onset of infectiousness. So suppose look at this timeline. So t is equal to 0. This is the time when an individual is getting some infection of COVID-19. And this is in case of COVID-19, the latent period is about 4.6 days. So during this period, an individual carries the virus, but he or she is unable to spread the infection. Incubation period represents the time between the occurrence of infection and the onset of disease symptoms. Here it is 5 days. So this is t equal to 0, that an individual is getting infection. And this is about 5 days. After 5 days, the individual shows some symptoms. So there is a period about half of a day, that is around 10 hours, where the infected individual does not show any symptoms, but he or she is infectious. Infectious period is defined as the time during which an infected individual is capable of spreading the infection. And in case of COVID-19, this period is on an average is about 14 days. And out of these 14 days, 5 days, 5 to 6 days, the infected individual remain highly infectious. Usually, an infected individual visit a doctor on an average 1 or 2 days later after appearing the symptoms. And it takes another 2 days to get the test report. Thus, around 3 to 4 days of the highly infectious period, that is out of 5 to 6 days of the highly infectious period, an infected individual spend 3 to 4 days before he or she is detected and isolated. During these 3 to 4 days, the individual remains in the society and do all things like other healthy individuals do, and spread infection to others who are in close contact. That is, from my point of view, is one of the most important reasons why controlling COVID-19 is very challenging and difficult. This also explains why random testing is very important for COVID-19. We have to identify and isolate COVID-positive patients as early as possible. In this case, the South Korean 3T principle, based on trace, test, and treat, is possibly the best option in controlling COVID-19 spreading in absence of a specific vaccine. If we cannot trace the potential infected individuals before 5 days or highly infectious period, it will be difficult to break the chain in absence of a vaccine. And that is why large-scale testing and random testing are very important. Here I present a flowchart of disease progression. We divide the total population of a country into 5 disjoint compartments, namely susceptible population S, and this susceptible population after exposure to infectious individuals join the latent class L or latent class E. Latent individual, if detected COVID positive, then join the symptomatic I class or join the asymptomatic class A if it is he or she is not detected. Some undetected individual may again join I class if later on shows symptoms and are detected as COVID positive. Individuals of I class either recovers and join R class or die due to infection. Most individuals of asymptomatic class recover from the infection. Each compartment has a normal death, and no death is considered in this asymptomatic class because if such issue arises, then the individual will be tested for COVID-19, and if it is positive, then he or she will join to the asymptomatic class. So based on this on this diagram, we construct a mathematical model, which is a deterministic model with this coupled of highly nonlinear differential equation. These are the rate equation of susceptible population, rate equation of latent equation, rate equation of asymptomatic infected individual. This is rate equation of symptomatic infected individual, rate equation, and recovered class. And we have also added an extra equation that determines the rate equation of death individuals. And this is the capital lambda is constant input through birth. This is M is the natural death rate. Beta is daily number of contacts per infectives. Kappa is the probability that infection transmits from an asymptomatic individual to a susceptible individual, and 1 minus kappa is the probability that infection transmits from an symptomatic individuals to a susceptible populations. This omega is the exit rate of E class, and delta is the probability that an exposed individual will join to A class. 1 minus delta is the probability that E will go to I class, and nu is the joining rate of I class from A class, gamma 1 is the recovery, and these are the all parameters. I have marked these 3 parameters, beta, gamma 1, and gamma by red color, because I have further interest on it. Uncertainty is obvious in a growing epidemic, and it multiplies if the disease etiology is largely unknown, as in the case of COVID-19. It is shown that there exists huge uncertainty in the reported COVID-19 infection rate. Uncertainty is almost certain in the proportion of detected and undetected case, as well as in the symptomatic and asymptomatic cases. There is a large variation is also observed in the uncertainty or in the infectiousness period and recovery period. We therefore consider such uncertainty in the previously 3 red color parameters, beta, gamma, and gamma 1. So we have added some noise or some error terms in these parameters. Beta has been replaced by beta plus some noise terms, where sigma 1, sigma 2, and sigma 3 are the noise parameters, and bi are the standard mutually independent Brownian motions. So based on these assumptions, we transfer our deterministic system to these stochastic systems, and we have this type of initial conditions. Since we are dealing with with some systems of nonlinear either deterministic equation or stochastic equation. So from mathematical point of view, it may be interesting to know whether your concentrating on these technical terms. Rather, I am giving some other results which may be more interested for common audience. So, basic reproduction number is probably the most important measure in epidemics. It defines whether a disease will grow in size or the disease will be eradicated from the system. So, and this basic reproduction number is defined as the number of secondary infection produced by an infected individual throughout the infectious period when introduced into a group of susceptible. So, if we consider that the basic reproduction number of a disease is 2, that means R0 is equal to 2, then it means that one infected individual marked by red color will produce 2 new infectives, and these 2 new infectives again produce each 2 new infectives, and this will go on. Therefore the number grows exponentially. So it shows one thing, that if R0 is less than 1, that means one infected individual is producing less than 1 new infectives in his infectious period, then it means that the disease will not be able to grow further. So if R0 is less than 1, it implies that the disease will go out or will die out. And if R0 is greater than 1, then it implies that the disease will grow in size. So based on this basic reproduction number, we can give some, we can prove some mathematical results. I have also omitted the proof of the results, but I am just showing the results. One can calculate through the next generation matrix that the basic reproduction number of the deterministic system can be expressed in this way. These are all system parameters. And we can prove that the deterministic system becomes infection free when the basic reproduction number, this R0 is, this R0 is less than 1, and the disease will persist if R0 greater than 1. We can prove this, this result. In case of stochastic system, we first define when the latent class will be extinct, in probability. So for the stochastic system, individuals of the latent class E are said to be extinct if limit t tends to infinity equal to 0 almost surely. So based on this definition, we can define that the stochastic system is said to be disease-free if there is no individual in the latent class. That means this definition holds. We can prove that the stochastic system will be disease-free if the basic reproduction number for the stochastic system, denoted by R0s, is less than 1, where R0s can be expressed in this way. And this is basically the asymptotic behavior of the stochastic system. One thing I would like to mention, that in case of deterministic system, we have some equilibrium points, but in case of stochastic system, we do not have any equilibrium point. But we can define the asymptotic behavior of a stochastic system with this theorem, that if ST, ET, AT, IT, RT is a solution of the stochastic system, and if these conditions are satisfied, then we can prove this result. This is basically the time average. This is basically the time average of distances between the stochastic solution and the deterministic equilibrium solutions. So This time average is less than equal to some constant G1, where G1 has been expressed in this way. Note that if C1 is 0, then G1 is 0. What is C1? C1 is max of the noises. So if the noises are 0, then right hand becomes 0, and in that case, ST will be equivalent to S star, ET will be equivalent to E star, IU equivalent to I star, and AU equivalent to this star. That means your deterministic solution and the stochastic solution will be coincide. So we have taken data from COVID-19.org. You can find the data of India from this website. This is a free website, and we have taken the data of India from 1st March to 6th September, that is 2 days before, and we have fitted the original data represented by this magenta color with our stochastic solution represented by blue color, and we have estimated the parameters like this. These are the parameters set for our system, and with this parameter set, we have estimated the daily cases for our country, and daily cases means we have plotted here only the I, because only I have the count. Undetected COVID cases, we don't have such accounts, so we have only plotted the detected cases that are given on the website. So these are the daily cases obtained from the stochastic model simulation, and we can see that the peak is expected something like here. This is the first week of October. That is the next week of October. We may expect, I am not sure, because this date is shifting gradually. And we can show that the distribution of this data looks like some Gaussian distribution or bell-shaped curve. Here 0 indicates the 1st March, and this is continues up to 600 days in absence of any vaccine. If there is no vaccine, it may continue up to 600 days. And this 600 days means October end 2021. And this is the disease extinction. As I given the definition of disease extinction in case of a stochastic system, that a stochastic system is said to be infection-free if limit t tends to infinity, it equal to 0 almost surely. And you can see that this is the peak per day, and this is the disease extinction in absence of a vaccine, which is about the end of October 2021. And you can see that the number of infected individual, if it attains the peak in the first week or in the second week of October, then the number of infected is very, very high. And this is, you can see that this is 12 to the power 10 to the power 4, means 1,20,000 or 30,000 per day cases in the first week of October. And this is the cumulative number. These are the actual data, and these are predicted cumulative numbers of I class. Again, I want to repeat that we have plotted only I class. That means those cases which have been detected by RT-PCR or any other confirmation test. And these are the 95% confidence interval. Cumulative confirmed case in October 2021 may be up to 1.31 crore in absence of any vaccine. And this is the case of our state, and you can see that these are the actual up to this. These are the actual data represented by blue color. You can see that last few days the number of new cases was was lower than the number of recovered cases. But after that, it again shows some increment, and again the peak may be observed on the first week of October, and the number of new cases may be around 4,000 per day. I am going to the next model. As we all know that there is no specific drug or vaccine that can cure the infection and protect people from the infection of coronavirus till now. Hopefully it will come within 2-3 months. It is therefore prudent to use the existing resources and control strategies in an optimal way to contain the virus spreading and provide the best possible treatment. Use of repurposing drugs along with the non-pharmaceutical intervention strategies may be the right way from my point of view for fighting against the ongoing pandemic. Repurposing of drugs implies that some drugs which are approved for the treatment of some other disease can be used effectively for the treatment of another disease. For example, in case of COVID-19, this dexamethasone, this is actually an immunosuppressor, are frequently used to treat arthritis and asthma patients. But it has been demonstrated that these drugs may also be used for critically ill COVID patients. And it has been proven that, that the mortality can be reduced by 1/3. So this is a very good thing for the treatment of COVID-19 patients. Another drug, this remdesivir, this is actually a drug for the treatment of Ebola virus, but it has shown positive result for the treatment of severely ill COVID patient. This is another drug. And the third drug is favipiravir. This is actually used for the treatment of influenza, may also be used for the treatment of mild or moderately ill COVID patients. So different countries like USA, UK, some European countries, and also our country, India, has approved this drug for the treatment of COVID-19 patients. In fact, India has approved these drugs just before 15 days back or 3 weeks back. So if we use these repurposing drugs in our mathematical model, we want to see how the use of these drugs may affect in the recovery rate or in the death rate of COVID-19 patients. So for this, again, we have divided the total population into 5 compartments, namely susceptible population S. This is latent class E, home isolated class IH, hospitalized class IC, and recovery class R, and there is also as a death class V2. V is the virulence of the disease. And this arrow diagram indicates that individual may go from this class to this class. Hospitalized infected may go this from to either to recovery class if the patient recovers, or join to the virulence class V if the individual dies due to COVID-19 patients. So again, based on this schematic diagram, we can propose a mathematical model. But before that, we introduce. So this is the deterministic model just based on the schematic diagram. So now we introduce these controls. In fact, 3 controls in this system, and this is the control system in presence of 3 controls U1, U1, U2, U3. These are the 3 constant controls, and its values lies between 0 and 1. The first control U1 actually is the reduction in the daily number of contacts due to lockdown, and U2 is the reduction in the transmission probability due to using face masks, maintaining individual hygiene or safe distance, or like this. And 1 minus, therefore 1 minus U1 and 1 minus U2 are respectively the effective daily number of contacts and effective daily transmission probability. The third and most interesting control is the control U3. This U3 actually reduces the death rate and increases the recovery rate due to the use of repurposing drugs. So we can find or deduce many other subcases depending on the values of U1, U2, and U3. For example, if we consider that U1, U2, U3, all three are 0, then it implies an epidemic model for COVID-19 before lockdown stage, that is before 25th March. Our lockdown started on 25th March. So there will be no control. So U1 equal to 0, that means there is no lockdown. U2 equal to 0, that is there is no mask use or maintaining social distance, etc. And U3 equal to 0, of course, there is no use of repurposing drugs. However, if we consider that U3 equal to 0, but U1, U2 not equal to 0, then it implies that there is no use of repurposing drug, because U3 measures the effect of repurposing drug. So U3 equal to 0 implies there is no use of repurposing drugs, and U1, U3 not equal to 0 implies that individual hygiene and lockdown are there. If U1 equal to 0, but U2, U3 not equal to 0, then it implies that U1 equal to 0 means there is no lockdown, and U2, U3 not equal to 0 implies that individual hygiene and use of repurposing drugs are present. And if you assume that U1, U2, U3, all three are not equal to 0, then it implies that all types of control measures are in the process. So we again analyze this mathematical model and give some results. The first result is again the basic reproduction number of the model, and we can compute that the basic reproduction number is given by this expression. So if note that if U1, U2, there are two controls, U1 and U2, but there is no U3, that means there is no third control, because whenever you calculate this basic reproduction number from the next generation matrix, then it depends on the infected compartment. Since the third control does not appear in the infected compartment, so the third control is absent in this basic reproduction expression. So if you put U1 equal to 0 and U2 equal to 0, then the basic reproduction number reduces to R0 dash, and this is given by this expression. And you can observe that this value is greater than the basic reproduction number in presence of control. We can again mathematically prove that the system becomes infection free if the basic reproduction number is less than 1. On the other hand, if the basic reproduction number is greater than 1, then the endemic equilibrium, that is the coexistence of infection, is possible in the system. So again, we have determined the parameter set for this system by fitting of curves as before, and we have obtained this parameter set for this controlled system. And the first figure is the variation in the basic reproduction number R0 of the COVID-19 epidemic in India. You can see that the value of R0 as on 24th March 2020 is around 1.87. That means each infected individuals were producing 1.8 new infectives during his or her infectious period. And this basic reproduction number goes down to 1.20 as of 31st May. This is the date when the lockdown was imposed in India, and from 1st June onward, partial removal of lockdown started, or unlock period started in phases. So as of 31st May, the value R0 reduces to 1.2 from its previous value 1.8. As of 27th August, the value further reduces to 1.11, but it is still greater than 1. That means the epidemic is still growing. So in the second phase, we have plotted the curve R0 is equal to 1. This separates the infection-free state where R0 is less than 1 from the infected state where R0 is greater than 1. So this is the separatrix. In fact, the two equilibrium, that is the infection-free equilibrium and infected equilibrium, changes their stability for R0 equal to 1. And we can mark the present value of the control U1 and U2 here by this red dot, and through the community involvement, we can push this value. If we can push this value from this region to a point somewhere here, then only the epidemic will be under control. And in that case, R0 will be less than 1. And this is the predicted cumulative COVID-19 confirmed, recovered, and disease cases in India for the next 1 month. For 1 month, I mean August 27 to September 25. We last updated this figure on August 27, and simulated our model till September 25 for different values of the control U3. U3 means the effect of repurposing drug. This simulation results shows that when U3 equal to 0, this is the curve where U3 equal to 0. That means if we do not use the repurposing drug, then the values after 1 month, that is on September 25, the number of death cases will be like this. And if we consider that U3 has a very low value, 0.2, then you can see that this is the predicted value of the death cases when the repurposing drugs has an effect, equivalent effect U3 equal to 0.2, and then U3 equal to 0.3, and the last one is U3 equal to 0.4. So it has been clinically proved that the value of U3 at least is 0.3. That is 1/3 of the death you can save if we use the repurposing drug. So if we consider that U3 is 0.3, then we have considered we have estimated the percentage change in the numbers of cumulative positive, recovered, and death cases due to repurposing drug therapy for different values of the control parameter U3. And these are the changes in the corresponding class. This is the infected class, this is the recovery class, and this is the death class. And this bar represents that if we do not use the repurposing drug, then the number of death will be this, and it will reduce by 2.39% if the value of U3 is 0.2. It will reduce around 5% if the value of U3 equal to 0.3, and around 7.5% if the value of U3 is 0.3. So if you consider that as experimental result shows that the value of U3 is 0.3, then India will save about 4,794 lives in the next 1 month, that is from that is up to 25th of this month, using the repurposing drug for U3 equal to 0.3. So this is huge achievement if we use the repurposing drug. And this is a more advanced model. I can just want to show you or explain the model, but I have not shown the result of this model. And you can see this is the susceptible individual. I must mention that every individual is susceptible, irrespective of his sex and age, because our immune system is not ready to fight against COVID-19, because this is a novel virus. So each and every individual is susceptible. So this is susceptible, and this is quarantined, and you can show that this is the latent class. This latent class arrives with the interaction of susceptible class or undetected class. So through interaction, they join to this latent class, or through detected class and interaction between through detected class and susceptible or quarantine class. Sorry, this is interaction between detected infected individuals and susceptible individuals. People may join to latent class. So there is two branches. Latent class may be joined to detective infectives through some confirmation test, or may remain undetected. We don't know the percentage or ratio or the fraction of undetected infectives. You can recall that some serological tests, especially IgG tests, were done in different metropolitan cities. And in case of Delhi, it has been shown that around 27% people have shown IgG positive. That means they have grown that is, the antibody has grown in their bodies. Huge population. That means 27% is huge population who have remained undetected, or somehow they have got some infection but have not tested positive. So that is the problem in controlling the COVID-19 patient. So there are two classes: undetected infectives and detective infectives. Detective infectives may be asymptomatic or mild, and they stay home for home isolation, and they recover from home isolation, or they may go to the hospital for if there is any complication. Again, detected infectives, at least 14% detected individuals need hospital treatments. So they go to the hospital for the treatment of COVID-19 patients. So from hospitals, either individual may recover and join the recover class, or may die due to infection, or may die naturally. And each compartment has natural death. So this is a more complicated mathematical model, but it is more relatively more general model, and one can construct such deterministic system or stochastic system based on this schematic diagram. So the one thing I would like to mention, that to get rid of this COVID-19 pandemic, we have to remain united and fight together to eliminate the infection from each corner of the world. We have to keep in mind that the disease started spreading from a market of Wuhan and eventually spread throughout the globe. So in combating the global pandemic, collaboration among industry, academia, and public health entities are very, very essential. So before I finish, I must acknowledge my co-researchers, Mr. Abhijit Majumdar. He is my research scholar. Abhijit Pal, he is from THSTI Faridabad. Dr. Devdatta Adok, he is my past PhD student. He is now in NDB University Agartala. Dr. Samrat Chatterjee, he is Associate Professor of Translation Health Science and Technology Research Institute. This is a DBT institute in Faridabad. And Professor Taposh Kumar Bala, he is actually a medical practitioner. And I must acknowledge the financial support given by the SARC. I received a project on COVID-19. The call was given by the ACRB on emergency basis. And thank you very much for hearing me. Thank you very much.
Thank you, sir. Thank you very much for the lovely informative presentation. I think we really enrich ourselves through this speech. Now the time of questionnaire. Sumitra Ghosh, one of our faculty members, will conduct this session. I request her to take care and share the questions coming in the chat box. Please, Sumitra, if you have any questions, please share with sir.
Good morning to all my respective sir and madam. But
Thank you
still
very
we
much.
have no questions, sir.
Oh,
Thank you, sir. All are saying that the
sir, I
representation is very
have one
nice,
question.
but
Yes,
still
yes,
we have
yes.
not such.
Yes, can we incorporate the delay as a delay the pandemic lockdown period in our model?
Yeah, you can definitely incorporate delay. In fact, you can incorporate multiple delays, because there are a significant delay in the recovery of severely infected patient. As I have mentioned earlier, that mildly infected COVID-19 patients recover uh, uh, within within a couple of weeks. But in case of severely infected COVID-19 patients, they require around 2 to 4 weeks. So definitely incorporate delay in the deterministic system as well as in the stochastic system.
Oh,
That will be a very good extension of the work. I think.
okay, sir. Thank you once again. I think you will be available to ask for if we need further. Thank you.
I am available up to 1 because I have an important meeting in our mathematics department. So I am with you up to 1.
Okay, sir. Thank you. Thank you, sir.
Thank you very much.
Now, I would like to
Yeah.
okay, please.
Department.
So let us proceed our program. Now, I would like to invite Dr. Kunal Chakraborty, a young scientist working as a scientist E and in charge ocean modeling of Indian National Center for Ocean Information and Services, that is INCOIS, Ministry of Earth Sciences, Government of India. Dr. Chakraborty received PhD from IIST Shibpur, Howrah on biomathematics. He has published more than 50 research papers in different national and international journals of high repute. He has guided 4 PhD scholars and 4 are pursuing PhD. In recognition of his outstanding contribution on modeling of marine ecosystem variability in the Indian Ocean, the Indian National Science Academy, New Delhi, selected him for INSA Medal for Young Scientist in 2017. He has been selected as a member of Indian National Young Academy of Science for 5 years in 2019 and awarded an Associate of the Indian Academy of Science in 2020. So, we are proud to have such a scholar with us. Let us hear his scientific talk on modeling physical biological interactions in the Indian Ocean and application to the potential fishing zone for forecast. Please, Dr. Kunal, I request you to deliver your presentation.
Thank you, Dr. Halder. Let me first share my screen. Yeah, is it shared? I guess.
Yes.
Hello, am
Yes,
I
sir.
audible?
Yes. No,
So, yeah, so my screen is visible to all of you.
fine. Fine. It is visible.
Yeah. Okay. So before starting my presentation, let me thank the organizers for providing me an opportunity to deliver a talk in this national webinar on mathematical modeling and its real world applications. And before starting, let me thank Professor Boiragi as well for presenting a very good mathematical model, and that too, which is very relevant considering the present pandemic situation. We are really enriched with this presentation. But what I'm going to present, that is little different, but indeed it includes mathematical modeling, and what I'm going to show, it will basically give you a test, or rather mathematical models on the earth system science. And at the end of my presentation, I'm going to show you a direct application of these models into a very interesting service that is being provided by our institute, which is popularly known as potential fishing zone advisories. I hope I am clearly audible to all of you.
Yes. Clearly.
Okay, so let me proceed. As you can see, the title of my talk is the modeling physical biological interactions in the Indian Ocean. So why Indian Ocean? The reason is the institute mandate is basically covered the entire Indian Ocean dynamics. So we are working on the dynamics of Indian Ocean, and we have couple of models that is being developed in-house, which is being used for forecasting several variables, which includes temperature, salinity, starting from the physical variables to the biological variables, which includes chlorophyll, oxygen, and other biological variables like carbon and so on. These specific applications are on the earth system science. So I'm basically taking you the basic fundamental descriptions of the mathematical models and how basically we are having the earth system science to work on this specific subject. So to start with, why we are basically working with mathematical models? What is the exact requirement? If we just ask this question ourselves, then the simple answer is this is nothing but a description of a real world system. Whenever we are talking about a model, basically we use to model a system, or rather a real world system, which and this is being modeled using the mathematical concepts and mathematical languages, which includes the differential equations and several other mathematical tools. So application of mathematics is not restricted into one or two areas. Everywhere in the world, wherever we are considering a real world applications, it is indeed mathematics which is being used to develop the models for starting from the understanding of the system, and then followed by providing forecast and all other services. So how we are basically going to develop such kind of a system, that I'm going to show you in the subsequent slides. So if you can see the next slide, this is talking about a climate system. So the major part of a climate system is consists of atmosphere, ocean, and the land. So we know the atmosphere, we are having wind, sun, and there are specific atmospheric models. These are available, and this is being frequently used to forecast the atmosphere. Then the most important part is again the oceans. Why it is most important? The reason is this is the area which is basically controlling, or rather the trigger the atmospheric component. So that's the importance of ocean comes into the picture. So we should have a very good understanding the ocean, so that we can basically predict in a better way the atmosphere. And obviously these are connected with land, which includes everything, our human intervention, and then trees, greenery, and everything. So this is a coupled system, which is in total we are considering about the earth system science. So our ministry is basically dealing with all the components of a specific climate system. So I am going to specifically show you the applications of mathematical models into the Indian Ocean. So if I'm considering a numerical model which is based on the atmosphere, so these are this is not at all the all components, but the major components are something like the wind, temperature, water vapor, and then indeed the radiations. So if I considering all these major components, these are connected with this kind of like transports, and then sensible latent heat fluxes, wind stress, and other parameters. So we need to take into consideration this kind of specific interactions. We are going to develop or build a specific atmospheric model. And why I'm considering atmospheric model, the reason is this is the atmosphere which is basically triggering the ocean. Why? How it is triggering? When wind is blowing, its specific is that blow of wind is having an impact on the ocean dynamics. So the entire dynamics is basically governed by the wind, how it is blowing, in which direction it is blowing, what is the strength of wind, and just several other factors. And then if I'm considering the radiation, when the sunlight is coming.
Dr. Kunal, please,
Yeah.
please share your screen in big mode, in full mode.
Okay. Yeah, now is it fine with you?
Yeah, fine.
Okay. Fine. Okay.
Mm.
So, okay. Now, after this atmospheric stuff, if I'm considering the ocean, so what are the major components? If I'm considering the physics, then the major components which basically govern the ocean dynamics are the ocean temperature, ocean salinity, and then the currents. And these currents, this is basically triggered by the wind. When wind is blowing, obviously that has a direct impact on the ocean currents. And if we consider the other factors like solar radiation and sensible and latent heat flux, these are basically the factors which is regulating the ocean temperature. And this is the most important component which is basically or subsequently regulating the atmosphere. So it's basically both way coupled system. basically atmosphere is governing the ocean, and the ocean is also governing the atmosphere. So it is two-way coupled. So when we are considering a model, we need to take into account both the components simultaneously. So initially what I am going to show you, it's basically how these models are developed and how we are basically using those models for the real-time forecasting. And thereafter, I am going to show you a direct application of this model into the potential fishing zone advisories, which is basically connected with the common people of India who are basically residing all along the Indian coastline, which is like 7,600 kilometer approx. So how it is going to impact the livelihood of common people, that I'm going to show you with as an application of this kind of models. Now, if I'm talking about the development of these models, or rather the model that is being used by INCOIS to forecast the ocean state, we are using a coupled modeling system called ROMS, that is Regional Ocean Modeling Systems. This ROMS is nothing but an ocean general circulation model. This is known as OGCM. There are several other models as well, but this is the model that is being developed specifically for excel the coastal applications. See, we can always talk about open ocean and coastal ocean. We can model the open ocean, but our activities is basically restricted within the EEZ, or rather most activities are restricted within the exclusive economic zone. So we need to basically consider our applications into the coastal oceans rather than the open oceans. So that's the reason basically ROM is designed for. ROMS has the capability to simulate the coastal ocean reasonably well, and that is basically helping us to provide the services that is being provided on regular basis from our institute. So this is the hydrodynamics, which includes physics, biology, sediment, sea ice, and all the other possible components that is being required for develop a model for Earth system science. So in this slide, what I'm going to show you, it's the minimum requirement to develop a model, using ROMS or any other mathematical models for simulating the ocean dynamics is, number one, you should have a grid. In the subsequent slide, I'm going to show you what are the grids and how are you going to have those grids. Then the forcing. Forcing means what basically regulating the ocean dynamics. So it is atmosphere, river, and all other forcings. And then see, when I'm talking about the mathematical models, this is nothing but highly nonlinear, some partial differential equations. So if you want to solve a partial differential equation, what do you require? You require the boundary conditions, the initial conditions. So these are the primary requirement to solve a nonlinear partial differential equations. So boundary conditions, initial conditions, and then you need to basically providing the climatological forcings. Since if you want to start a model from the cold state, then you need to come to the hot start or the present state with the help of the climatological simulations. So these are the primary requirements when you are talking about a ocean model, or when you have a requirement to simulate ocean dynamics. Now, if you see the models that is being developed by INCOIS is something like this. We have a global model. If you can see in this slide, it includes all the global oceans, starting from the Indian Oceans, Pacific Oceans, Atlantic Oceans, then you have Southern Oceans, and then Arctic and Antarctic, all the oceans. So it's a global analysis, or rather the global model. Why do we require global analysis? The simple answer is our climate is not restricted within the Indian subcontinent. This is being affected by the Pacific, Atlantic as well. So if you really want to simulate the ocean dynamics reasonably good, you should have considered that kind of a global analysis for providing at least the boundary conditions or the necessary information to simulate the regional dynamics. So that's why we started with a global analysis. Then subsequently, we have started with the Indian Ocean forecast. So this is our regional analysis. If you can see, this global analysis is providing the boundary to the regional analysis or the regional models. And then subsequently, it is confined to our area of interest, that is the west coast of India. It's a very high resolution models, then the southeastern Arabian Sea, and then followed by the Bay of Bengal. So these are the areas where our interest is basically focused on. So that's the way the entire modeling system is coupled. Now let me give you an important information here. When I am talking about this kind of a modeling system, it is not basically possible to run this kind of a model in our local systems or the local workstations. In order to run this kind of ocean models, you should have high performing computing systems. So thanks to the Ministry of Earth Sciences, we are right now fourth position in the global scenario, where our computing facility providing us 1.5 petaflop computing facilities. We are having two high performing computing system. One is located in Noida, another is located in Pune. These are known as Proteus and another is known as Mihir. So these are the systems which are basically being used to run this kind of models. So we are basically sitting in Hyderabad. We are using National Knowledge Network, that is commonly known as NKN network. Through NKN, we are connected through the high performing computing systems. We are running our models into these HPCs, and then subsequently the analysis being provided to the common people or the administration by the operational team on regular basis, that is 24/7. Now the next slide, that will give you an idea about the Indian Ocean regional model. If you can see the figure, the left side topmost figure, here you can see that I have divided that specific domain into grids, and the domain that is being considered for this model is 30° east to 120° east, and then 30° south to 30° north. So this entire Indian Ocean is basically divided into multiple grids. Now, how do you divide that? That is being divided considering the resolution what you are basically looking for. So in our case, what we have done a horizontal resolution of 1/12°, which is almost 9.5 kilometer in horizontal direction. So if I am considering 1/12°, then considering that specific horizontal resolution, the entire grid is basically divided into multiple grids. And then apart from that, this is one level, that is the surface you are looking for. But the Indian Ocean, if you consider, it is basically having the depth almost 5,000 meters. So the entire depth of the Indian Ocean, that is vertically divided into 40 sigma levels. So when I am considering the surface, this is at the 0th depth. Then we are having several other layers. One is 5 meter, then 10 meter. Then subsequently, it is basically divided into 40 such vertical levels. Since our interest is mostly confined into the upper ocean dynamics, we have basically used 21 such vertical levels up to 200 meters of depth, and then subsequently the rest 19 levels being distributed to the rest vertical depth. So this is the preliminary descriptions of the horizontal resolution, vertical resolution, and then followed by the boundary. If you can see this specific domain, in the northern side, you don't have any ocean. So this is basically covered by the land. if you can see the western side, here also this is covered by land, but you can see the eastern side. This is basically connected with the Pacific Ocean through Indonesian through flow. So you have to have a boundary condition to be prescribed to solve the differential equations into this eastern side and as in the southern side as well. Then eastern and southern boundary, apart from that, this is, you can have a model with 1/12 degree of resolution. Next, if I am considering the models which are being developed for the coastal applications, we have three such models. One is specifically applicable for the west coast of India, that is being basically, so here it is shown into the blue boxes. Another is for the southeastern Arabian Sea, considering the commercial activities being taken place in this area. This is basically covered by the green line, and then the Bay of Bengal, which is basically covered by the magenta line. But the difference is here, these specific domains are having much higher resolution, which is 1/48 of degree. So you can consider almost 2.25 kilometer resolution grid size being taken for the coastal applications. And the reasons are, you need to have this kind of high resolution to resolve the ADs or the mesoscale as well as some mesoscale structures using the models. So this is the major difference in case of coastal applications. And here I would like to mention the coarser resolution or the Indian Ocean model, being it is providing the boundary conditions to the coastal applications. So the global models are providing boundary to the Indian Ocean model. Now Indian Ocean model is basically providing boundary conditions to the coastal applications. So these are all nested with each other, and that nesting is very important to resolve the ocean dynamics. Now, whatever I have already told, this is specifically based on the physics. So what you can resolve, you can have the ocean temperature, salinity, then U component, or rather the zonal component of the current, meridional component of the current, and the sea surface height. So these are the specific state variables which are being resolved by the models, and this includes the ocean physics. Now, in addition, if you would like to solve the ocean biology, then you should have another model which is further coupled with this ocean physical model. So we do have such kind of models which are known as the ecosystem models. So to give you idea about how these ecosystem models looks like, you can see a very simple coupled physical biogeochemical models. This is a schematic diagram. If you can see here in the right side, these are the very basic variables that you need to consider for developing an ecosystem model, which includes the nutrients. So these nutrients is not only confined into one state variables, it is basically further divided into several nutrients like nitrate, nitrite, silicate, phosphate, ammonium. So all those specific nutrients are having a different state equations. But overall, you may consider those specific nutrients as a component, that is nutrient. Then followed by phytoplankton. This phytoplankton is basically coupled with this chlorophyll. So in the presence of nutrients and in the presence of sunlight, you know the process of photosynthesis. So the photosynthesis will take place and you will have the growth of phytoplankton. So this phytoplankton is another component. Then if you have a sufficient phytoplankton, then the zooplankton will come to that area and you will have this phytoplankton being used by the zooplankton for their survival. So these zooplankton and phytoplankton, these are also basically divided into several classes. But here I have, in this specific slide, it is being shown in one component. So this zooplankton is also basically considered the fishes as well. Now these deteriorators, phytoplankton and zooplankton, both within a certain time it will basically die. So when it's basically dies, it will basically decomposed and coming down towards the ocean bottom and in the form of deteriorators. So this is the very simple schematic diagram of a ocean ecosystem model. Now this is specifically governed by the physics, ocean physics. How it is governed, you can see when you have a sunlight, that is the most important source of having photosynthesis. So you should have the solar radiation, and solar radiation will change the ocean temperature dynamics. So this temperature will basically regulate the growth of phytoplankton. Then the currents, when you have an advection, the phytoplankton from one place will get advected to the another place. So accordingly the productivity of the ocean will be governed by the ocean currents. Then another most important part is the vertical mixing, or rather the diffusion that is being taking place into the inside the ocean. So it is not like that productivity or the growth of phytoplankton that is being taking place only in the surface. It is basically taking place till the euphotic depth. Euphotic depth, I mean to say, up to the depth to which the solar radiation can penetrate. So you will have to consider the growth of phytoplankton till that specific depth. So it's basically coupled in these ways. So physics and biology, these are coupled into each other. And the objective of that specific talk is to show how these are coupled and how good we are simulating that ocean dynamics, and how we are providing or how we are utilizing those models for the generating our services for the common people. So the major processes that are includes, its biological processes includes growth, death, photosynthesis, grazing, bacterial regeneration of nutrients. And the physical processes that are govern the biological activity, these includes mixing, transports, that is by currents, tides and winds, light, and obviously RC interactions. It is basically providing the winds, heat fluxes, precipitations and all. So these are the major processes. So we need to consider all these processes when we are talking about an ocean model, or rather a coupled ocean ecosystem model. This is a like schematic presentation how the dynamics looks like. If you just see the C as the concentration of any biological state variables, so DDT of that C is nothing but the sources term, that is the inputs from nutrients or the river or the sediments, whatever sources of that specific biological term, and then the sinks when it's basically dies and all these specific sinks, and obviously the transfer. It is not like in one grid only the source or sink is restricted. The physics will basically transfer the biological variables concentration from one grid to another grid. So that includes the typical dynamics of a specific biological state variable. Now if I'm coupled it with the physics, how it looks like, it is basically looks like this way. So it is del dt of C is nothing but the advection term, then the turbulent mixing term, and then the biological dynamics, whatever we have shown in the previous slide. That is the gain and in the loss, or rather the source sink with the transport terms. So this is a typical representation of a coupled dynamics of any specific biological state variable, or this is basically known as advection diffusion equations. That is even in the population dynamics we are also exploring this kind of an equation. So this part is the physics and the right hand side is the biology. Nowadays there are several conceptual models that is being developed, and these models now considering even 33 to 36 different state variables in the ecosystem part only, which includes like different size and species of phytoplankton, different size and species classes of zooplankton, even detritus also, like large detritus, small detritus, then different type of predators, which includes like specific type of fishes, and then the bio-optical properties are also getting considered, and on top of that the entire physics. So now you can imagine the complexity of that kind of a system when you are going to solve this kind of an model, what kind of complex system you are attempting to solve using the system. And that is the reason why do you require the HPCs, why it is not possible to resolve this kind of an equation in your local PC. I'm a little bit faster, or I just slow down a little bit with the space.
Okay.
No
problem. It's okay.
It's okay. Okay, fine.
You can.
Okay. Now, if I'm talking about our ecosystem model, which is being coupled with the ROMs, that is known as ROMs Fennel ecosystem models. So this is the typical schematic representations of the ecosystem models that is being coupled with our inquest system. So it includes these state variables which have the detritus, phytoplankton, zooplankton, oxygen, chlorophyll as a state variable, and then all the possible nutrients, and how these are connected, how the complex connectivities are that you can imagine from that specific slide. I'm not going into the details of that connectivity. Rather, I'm going to show you how it looks like when you solve this kind of a complex systems, and how are you going to validate your system. What are the observations being available with you to validate a system? See, model can be developed. You will have an output, but how reliable your output are, that you need to validate with observations. So in the subsequent slide, I'm going to show you that. You can see this is the spatio-temporal variability of SST in the seasonal time scale in the Arabian Sea. You can see the map. Probably you are not familiar with the map, but this is the map of the Arabian Sea. It includes the entire Arabian Sea. I could show you the Indian Ocean, but intentionally I am putting the Arabian Sea. The reason is, if I am having the entire Indian Ocean, then it would be really difficult for you to understand the difference what I would like to show in this specific slide. So that's why I have enlarged that specific slide for the Arabian Sea. So you can see there are 3 columns here. The first column is ROMS 1/4. I'm going to tell you what it is meaning. Then this TMI. This is nothing but the observations. So what kind of observation it is? This is nothing but the satellite observations. So we have here in INQUISE the ground stations, where we are receiving real-time satellite observations in our ground stations. So this is a satellite-based observation of ocean temperature. So the sensor that is being installed into the satellites, and when it is capturing, when it is basically passing through the Indian Ocean, it captures the ocean temperature, and subsequently this is being transmitted to our ground station, and from that we are having this kind of direct observations from satellite. Apart from satellite observations, we do have in situ observations as well, that I'm going to show you into the further slides. So the middle panel is nothing but the observations, or rather the satellite observations, and the right hand side panel, this is basically showing the ROMS 1/12. Now the difference between the left and the right slide panels is both are model simulated, but ROMS 1/4 and it is ROMS 1/12. The difference is in the resolution. 1/4 means when we are solving an ocean model with 1/4 degree, it means the grid size is almost 25 kilometers. And when we are solving an ocean model with 1/12 degree horizontal resolution, here the grid size is approximately 9.5 kilometers. Why it is important to have high resolution? The reason is, I have already told you, you need to resolve mesoscale dynamics. Otherwise, it would be very difficult to resolve the ocean dynamics reasonably well with your system. So that's the reason we are talking about the resolution of the ocean models. So you can see the seasonal behavior, like if I consider the DJF, it is basically considered as the winter monsoon. In terms of physical oceanography, it is known as the winter monsoon, that is December, January, February. Here in the northern Arabian Sea, specifically, you can see the cooler temperature or cooler ocean temperature. Even you can see here also, this temperature is cooler. So that's a specific cooler temperature is also visible in the satellite observations. Then if I am considering MAM, this is nothing but March, April, May. This is spring intermonsoon. The spring intermonsoon, this is here, this time you are having temperature is in higher side. So ocean is basically warming that time. And then JJAS, that is June, July, August, September. This is specific time when we considered the summer monsoon. So during summer monsoon, here the Arabian Sea is having the upwelling. The major physical process which is basically govern the ocean dynamics is the upwelling. You can see the signatures of upwelling into the Western Arabian Sea as well as in the Eastern Arabian Sea. So these signatures are captured by the models. And then ON, this is nothing but fall intermonsoon, that is October, November. So that time, this is the transition, like from summer to winter, this is the transition monsoon. So this is the way, and what I am showing, this is the surface temperature. So that's the way basically we are making use of satellite observations to validate our model and then go ahead with the subsequent analysis. Now, this is the simple spatiotemporal comparisons. How good it is doing in terms of statistics, that is being shown in this slide. If I am just putting the RMSE and correlation, it looks like this. If you can see ROMS 1/4, the mostly the RMSE is somewhere it is going up to 2 degrees centigrade. Whereas in case of ROMS 1/12, mostly it is restricted within 1 degree centigrade. Or even the the most important areas, that is the Indian part or the west coast of Indian or Eastern Arabian Sea, it is restricted even within 0.6, 0.8 degree centigrade RMSE. So that's the difference we are making when we are going for the higher resolution models. And the same RMSE improvement is reflected in the correlation as well. If you can see there, this is the correlation when we compared with the observations. Now, if I'm talking about the in situ observations, what kind of observations we have? We have several kind of observations, which includes autonomous floating observations through instruments. We are having ship-based observations. So like we are having different teams who used to venture into the sea. They used to be there into sea for like 30 days, 40 days. They used to collect several samples. They used to operate several instruments when they are on board, and we used to collect the observations from ocean itself. And apart from that, we are having satellite observations. So we do have different kind of ocean observations with us. And INCOAS is basically national oceanographic data centers. We do have several data available with us, and on request, it is freely available to the users for making their research. So anybody if interested on this kind of research or would like to make use of ocean observations, they can directly communicate through the channel which is being described into the website. So here what I am showing in this specific slide, this is an Argo float. So I'm told you like autonomous instruments. You can see in January 2012, we deployed one Argo float in this location. And it is basically programmed in such a way that every 10 days, it will basically sample the entire ocean profile. Mind it, what I am talking is profile. So it will go deep up to the 2000-meter depth. And then when it is coming up towards the surface, it will basically record the ocean temperature, salinity, chlorophyll, oxygen, and whatever possible sensors are installed with that specific float. So if you can see, when we deployed that, it is basically started moving, and these dots, these are the profile locations. So total 141 such profiles being collected by this specific Argo float. And this is the trajectory of that Argo float when it is moving from ocean. So from there it is started, and then it started moving with the ocean dynamics, and then finally it ends here in December 2013. So 2 years of Argo floats data are available here to show you. So this is just for presentation purpose. I am showing one such Argo. Right now we have like almost I think more than 200 such Argo floats deployed into the Indian Oceans, and those data are being frequently used for not only for validation but also for assimilation into the models. So we have a method called data assimilations. So we can assimilate the observations into the model to improve the forecasting capabilities. So there are several requirements for those kind of ocean observations. But here what I am going to show you the capability of the model when I am comparing the ocean dynamics. And apart from that, another observation is Court Station, that is Kochi time series observations. So here we have 10 locations where we collected ocean data for different stations. So 1 year of such locations being collected, that is also used to make the comparisons. So you can see initially these comparisons. Okay, now these are the boxes. You can see I have taken few boxes here to make the comparisons. Why you have taken the boxes? The reason is these are the areas when the biological activities are more pronounced, like you have more seasonal biological activities in these boxes. So you can have a better understanding how good biology is basically varying with that specific area. So the first slide, it is showing ROMS 1 by 4, ROMS 1 by 12 with MODIS. MODIS is nothing but the satellite observations. So MODIS is, you can see this is the blue line. ROMS 1 by 12, it is in the red line, and 1 by 4, it is in the black line. So this is climatological comparison being made. You can see 1 by 12 is doing reasonably good when we are having a comparison with the satellite based observations. In the next slide, you can see this is the in situ based observations, that is the Courts time series. Here you can see ROMS 1 by 4, the nitrate, when it is the time when upwelling is taking place in the Kochi or in the southeastern Arabian Sea. So the upwelling is taking place, and ROMS 1 by 4 do captured that specific upwelling. But if you can see the upwelling peak and the specific shape, it is basically missing with the observations, whereas 1 by 12 is doing much better job when we compare with 1 by 4. The same thing is observed when we compare with the in situ chlorophyll data. So this is 1 by 4, this is observations, and this is 1 by 12. And another important thing is here you can see here 1 by 4 is completely missing the low oxygen water which is coming towards the surface. You can see almost 550 micromole per liter oxygen coming during the upwelling time in the Kochi coast, which is well captured by the 1 by 12, but that is completely failed by ROMS 1 by 4. So these are some kind of an importance why we are basically going with the high resolution model, though it requires more computational resources. Then this is the time depth comparisons with the Argo. So let me just tell you how it is. So first slide, first panel, if you can see, or rather the top panel, this is made using Argo. So I told it is an autonomous profiling floats. So in one location, it is having the profile. Then it is moving with the ocean dynamics. Another location, you are having another profile. Then it is moving with ocean dynamics. Then another location, you have another profile. So such 141 profiles, if you club together, then the first top panel you can have. So, and it is shown up to the 100-meter water depth, or rather the upper ocean. You can see the presence of deep chlorophyll maxima till the depth of 50-60 meters, and it is seasonally varying. So the same thing is being plotted with ROMS 1/12 and ROMS 1/4. So you can see overall ROMS 1/12 is doing much better job, whereas in some places you can see here the magnitude is basically overestimated by the model. But you can see the depth and the presence of deep chlorophyll maxima that is well captured by the model. This is a similar comparison with in terms of oxygen. So this is the presence of low oxygen water in the Arabian Sea. If you just search the literature, you can see several articles which are talking about the oxygen minima zone. So this is basically the core oxygen minima zone in the Central Arabian Sea that is being well captured by the ROMS 1/12, whereas ROMS 1/4, this is completely basically failed to capture that oxygen-less waters. So these are the in situ based measurements that is being used to make the validation of our model. This is a specific animation which is showing how throughout the year the changes, surface chlorophyll is basically getting changed. See, this is the winter time. If you can see the change in the time, it's basically moving. So as I told, December, January, February, winter time, you are having a pronounced chlorophyll bloom in the northern Arabian Sea, or basically northeastern Arabian Sea, or off Gujarat. Then when the summer monsoon is basically appeared, that is June, July, August, September, that time you have upwelling into the southeastern Arabian Sea, and you can see that features being captured by the model in the southeastern Arabian Sea. And then slowly that upwelling in propagates towards north, and with the transition of southeast summer monsoon, again it's basically vanish, and then you are having fall winter monsoon, and after the fall winter monsoon, again you have winter monsoon, and you again bloom, it will appear in the northeastern Arabian Sea. So that started appearing in the northeastern Arabian Sea. So that's the animation which is basically showing how surface chlorophyll is basically varying with time. So that's whatever I have told. This is the model that is being developed by our institute for basically generating the services that is being used for the common people. Now there are several services that is being provided to the common people, out of which the more important service is known as Marine Fishery Advisory Service. Why it is more important and how it is basically making a difference, let me tell you. These potential fishing zones are identified in the oceans. Why it is important? See, if a fisherman is basically going for fishing activities, and if you are in the ocean, then 360-degree angle, everywhere you can see only water. So if you don't have any information where you can get more fish, you can simply make your attempts to catch fish. But ideally, what is going to happen? You will be end up with low fish catch. And at the same time, whatever basically fuel you are going to make use for fishing activities, that amount is also increasing. But if you know before going for fishing activities, what are the potential areas where the school of fish are available, and if you can simply go to that area, then what is going to happen? Your total fish catch is going to increase, and at the same time fuel cost will come down. So not only it is going to help you in your economy, or rather the blue economy, and subsequently from the environment perspective also, you are basically reducing the carbon dioxide. So that's the direct impact of potential fishing zone advisories into the society. So these potential fishing zones are identified as the relatively narrow zones into the ocean where the horizontal gradients of physics and biological properties of the oceans are enhanced or changed. So there are methods to identify those areas, which areas are basically detected using satellite as well as model data. And then on regular basis by 4 p.m. every day, we used to send all the coastal states that information for the fishermen. So right now, 9 lakh fishermen are registered with us, and we do have 9 lakh mobile numbers of fishermen, and we directly send those information to the mobiles of the fishermen. Apart from that, we are having EDB, electronic display board, being installed into several coastal areas, and the district administrators, they are also being provided these informations on regular basis from the institute, and that is being done by the operational team of INCOAS. So even if I'm talking about the West Bengal, in Digha, if somebody can, I don't know whether you can basically notate it or not, there are electronic display boards being installed by INCOAS, and there those informations are being provided on daily basis, and that is basically being administered by Digha Fishermen Association. So this is one such examples, but all along the Indian coastline, these informations being provided daily, and that too in regional languages. The reason is, if I am providing those information in English to a fisherman, it is not that much helpful to a fisherman. So considering the regional need, we basically translate that information into the regional language and then being provided to the subsequent fisherman state. So for that purpose, the major parameters that is being used as of now by INCOAS is the surface temperature, SST, and the surface chlorophyll. So how are you going to detect a potential fishing zone? Is something like, if you just have a image of surface temperature, you can identify the areas where you have cooler temperature. Cooler temperature means the subsurface water somehow come to the surface, and subsurface water is always having, if you go the temperature profile, it will show you the subsurface temperature is cooler than the surface temperature. So the cooler water is coming to the surface, you have a cooler temperature, and in this cooler temperature there is a clear gradient can be seen. So that gradient is being used to identify those areas. And now on the same time, if there is an enhancement of chlorophyll in the same area, it means there is sufficient food available for the fish to aggregate that area, and that can also be seen from the satellite images. So if you club together, you can identify those areas as the potential areas for fishing activities. So those are being identified by INCOAS on regular basis, and this is being satellite that are used. One is NOAA FHRR and another is MODIS Aqua. These are all foreign satellites, and apart from that, we are using our ISRO satellites, that is OceanSat 2 or OCM. So all those satellites data, we are directly having access on real time, that data being processed and subsequently by the end of day being disseminated to the concerned agencies for further dissemination. So next, this is the criteria that is being used to detect that kind of gradients. For thermal fronts, we are basically use Kailu-Karninan algorithm, and for the surface chlorophyll, we are using Canny algorithm. So that's the algorithm being used. Now, what are the issues that are having or needs to be taken care of, or how a model can be used to basically resolve those issues? So you can see, I have already told, we are using satellite data for generating that specific potential fishing zones. Now, the major problem is the cloud cover. So if you have an acute cloud cover, it is not possible to have the satellite data for the entire region of your interest. So there are data gap, and that is specifically happening when you have the summer monsoon. Summer monsoon when you have the rainy season. So you have a severe cloud cover. So we are having data, but these data are basically very sparse. You don't have a continuous data set for generating these specific advisories. Apart from that, dissolved oxygen you cannot get from remote sensing or from the satellite. So you should have oxygen data incorporated into the system for better identification of potential fishing zones. Now, if I am talking about subsurface, satellite can only provide you the surface features, that is your chlorophyll, surface chlorophyll and surface temperature. What about the subsurface variation of chlorophyll, subsurface variation of temperature and oxygen? So that also needs to be taken into account. So the model that is being developed by INCOIS, that is being used to overcome these outstanding issues, and we have graduated the PFG advisories into PFG forecast. So on the real time, we are using satellite data to generate advisories, supplementing with the model data, and then subsequently we are also providing 24 hours forecast of potential fishing zones. So that is basically giving us an opportunity to manage the coastal resources in a better way in the climatic change environment. This is the map where you can identify, like understand how we have divided the entire coastline for generating these services. Here you can see the top northern box. The West Bengal box is basically divided into two boxes. One is small, this box, another is this box, which basically includes the Odisha also. Then we have North Andhra Pradesh, then South Andhra Pradesh, then you have Tamil Nadu. Tamil Nadu is also basically divided into two boxes. Then here you have Kerala, here you have Lakshadweep, you have Goa, then you have Karnataka some part, Maharashtra, then Gujarat. And here we have considered the Andaman and Nicobar Island as well. So we have such kind of 14 boxes separately divided for generating those services and to provide into the corresponding regional languages. And the model that is being used is basically showing into these red boxes. These are the coastal models being used to basically supplement that service. So that's the schematic diagram. If you can see how we have developed that service is like this. The satellite data is basically coming from this. We are having ROMs developed, which is coming like this. So ROMs and satellite data, we are generating the advisories. These two are the advisories. And then finally, these are the areas where you can go for the fishing activities. So you can see with geolocations or the latitude and longitude, you can tell a fisherman you can go in this area for fishing activities. So that is the way we are basically generating this service, and then followed by this is the dissemination mode. So we basically use all possible modern technology to disseminate that service. And this is the paper, Modeling of Marine Ecosystem in Regional Scale for Short-Term Prediction of Satellite-Aided Operational Fishery Advisories in Journal of Operational Oceanography, that is being published in 2019, Chakravarti et al. Here you will get the entire details of that specific service. So that's the algorithm that is being used to make that specific service. The same thing, whichever graphical way we have shown, that is being provided into the tabular form, and the advisories and forecast that is being disseminated with multilingual delivery maps and text, and that is basically being provided to the fishermen. And then for validation and feedback, we basically used to conduct several user awareness program. During that time, we basically listen our users about their need, and accordingly basically we are keep on improving our services. So that is the direct application of an ocean model, or rather a mathematical model, into the application, or rather the real world applications, which is directly impacting the livelihood of the Indian fishermen. So that's all I had to say. Thank you. If you have any questions, please go ahead to ask.
Thank you. Thank you, Dr. Kunal. We really enjoy your high data-oriented rich presentation. We really
Thank you.
enlightened. Now I request for the questionnaire session. Sumitra, please, if you have any question in the chat box, please share with us. Sumitra?
Yes, sir. Good afternoon, sir. But there is no such question, sir, still now. All are enjoying and they're telling that a very good discussion, but no
So
questions
there are
at
two
all.
possible scenarios. Either they have understood everything or they didn't understand anything.
It's really. Sir, have you any question? Dr. Koidagi?
I just hearing the very good presentation of Kunal because this is very informative and there are there are lots of simulations and I am afraid to think about the model. If anyone see the model in physical sense, then he or she will understand what are the scenario is going behind the simulation results.
Yeah.
But this is very good application of mathematics in real world applications. Thank you very much, Kunal. Thank you very much.
Yeah, thank you. Thank you for your nice words.
Thank you. Thank you, Dr. Chakraborty. Now we are waiting for the last lecture session.
Yeah,
Madam
thank
Dr.
you once again for providing me this opportunity.
Oh, thank you. Thank you. Thank you from our side also.
Welcome.
So I request Madam Dr. Neelam, Assistant Professor of the Department of Applied Mathematics, Delhi Technical University, which was formerly Delhi College of Engineering. He received PhD on mathematical modeling from IIT Roorkee in 2004. He has published near about 30 research papers in different national and international journals. Her field of interest are biofluid mechanical dynamics, mathematical modeling and simulation, diabetes prevention and control, infectious disease. So, we don't late to hear her research experience. Today, Madam will deliver lecture on mathematical modeling approach to cause and control strategy for infectious diseases. So please, Madam, I request you to deliver your presentation. Madam. Hello. Hello, it's not audible, Madam.
Am I audible?
Yeah, Madam. It's audible.
Okay. So again, I'm thankful to the organizers, Principal Hooghly Women's College and Dr. Biswas for providing me this opportunity. In fact, I also owe a big thanks to the organizers to provide me the opportunity to attend the lecture of Professor Bairagi. You know, Professor Bairagi, I look forward
Madam,
for
your
your
sound is breaking. Madam, your sound is breaking.
Okay, just a moment. Is it okay now?
Yeah.
Is it okay now?
Yes, Madam. Now right.
Okay. So, I mean, it's my privilege to attend the lecture because
Sound is not there, I think. Hello. Madam. Your sound, it's not audible, your sound. But we are not audible. Hello. Chirantan. চিরন্তন, শুনতে পাচ্ছ সাউন্ডটা? Networking problem. I think so. It may be. It may be. She's taking a minute. It's really a big problem, I think, in today's, because in such type of webinar, a huge amount of data is required. There are a huge amount of network required. I think Madam is disconnected. Yeah, he joined. Hello. Hello, it's still not audible. Okay. Hello, sir. I think Really sorry for this unwanted situation. I think there is a thank you, Dr. Nandan Boiragi. Thank you so much for your presence. So, Chirantan, how can you proceed? Mm, mm, mm. Dr. চক্রবর্তী, হ্যালো,
Yes, please.
কি করতে পারি বলো?
কি হলো, মানে উনি কি কানেক্ট হচ্ছেন না?
নেটওয়ার্ক প্রবলেম মনে হচ্ছে কোনো একটা।
আপনি একবার কথা বলে দেখুন, মানে যদি উনি কিছুটা ম্যানেজ করতে পারেন, দেন প্রবাবলি ইউ ক্যান ওয়েট ফর 10-15 মিনিটস।
আমি ওকে ফল করতে বলেছি গুরুদাসকে। গুরুদাস আছো তো? গুরুদাস
অডিও বন্ধ গুরুদাসের।
গুরুদাস শুনতে তো পাচ্ছে। গুরুদাস শুনতে পাচ্ছ?
রিপ্লাই করলে আমরা শুনতে পাবো না তো।
গুরুদাস তোমার অডিওটা অন করো। হ্যাঁ গুরুদাস, গুরুদাসের নেটওয়ার্ক প্রবলেম হচ্ছে। ও স্টপ করো। হুম আমার
এটা
মনে হয়
স্টপ।
এটা স্টপ দ্য লাইভ সেশন। দেখো চিরন্তন